In Chem 1, we talked about activation energy. You saw the activation energy graphs. I'm going to go over that with you as well today. But when reactants collide, if they collide with enough energy, they can turn into products. Some things have a low activation energy, which means it's easy for them to turn into products. Some have a high activation energy, which means it's difficult for them to do that. And if it's easier to do, it will happen faster. If it's harder to do, it will happen slower. And that's what gets us back into this overlying topic of reaction rate for this entire unit. Now, collision theory is one of the topics that we have on our AP topic sheet. And what that says is the rate of a reaction is proportional to how many collisions occur. The more collisions you have, the more likely the reaction is going to occur faster. Think about ways that we can increase collisions. We could heat things up, because when you heat things up, they move faster, they collide more often. We could increase the concentration of a solution, because if a solution is more concentrated, there's more solute to make collisions. If it's a solution in a solid, we could grind up that solid, because now we're increasing the surface area, allowing more collisions. So no matter how we do it, stirring things up, if it's in a solution, can cause more collisions as well. So I say similar to kinetic molecular theory of gases, because the idea of we get them to move faster, they're more likely to collide, more likely to react. However, not all collisions can lead to reactions. I like to use the example of if I were to throw a baseball at a window, I could probably break that window. But you know what? I bet if you told me to not break that window yet throw a baseball at a window, I could do it as well. A nice little soft throw. I have to hit it hard enough. And that's part of what the collision is as well, is if you don't hit it hard enough, it's not going to happen. Or you have to hit it the right way. Because if you don't hit it the right way, if it's a glancing blow, which I know this for a fact because when I play baseball with my son in the backyard and I pitch to him, I have to try to put him in a corner where he has enough room to hit it into the yard. But hopefully when he fouls it off, because he's late often on his swings, he doesn't foul it off into our windows. And unfortunately, he does hit our windows, but it's not a direct blow. It's always a side blow that prevents it from actually breaking. Because I'd get in a lot of trouble for that. He wouldn't. Now, how does a chemical reaction occur when things collide? I like to think of this as symbols crashing into each other. That when things collide, there's vibration. Just like when you collide symbols, there's vibration as well. Now, if you vibrate or shake a molecule too much, those bonds can break. New bonds can form then in their place. I think that might be the last thing I point out on the bottom here. If you have enough vibration, you can break those bonds. But if there isn't enough vibration, the bonds won't break. So you have to hit them hard enough. And if the pep band is playing the national anthem and the person doing the cymbals just barely taps the cymbals together, no one's going to hear the ch part, which is what most people sing along to. Boom, ch. They don't actually sing the words, right? Yeah. So if you have a timid cymbal player, which I don't know any percussionist that's timid, I think to be a percussionist, you have to be angry and loud. Band people, is that another thing that we can agree upon? Come on. I mean,
our cymbals are pretty enthusiastic.
You gotta be. But if they're not supplying enough energy to get enough vibration to get a loud enough crash. When things collide, if they don't collide hard enough, nothing's gonna happen. They're just gonna bounce off of each other. Good here. Okay, so remember this graph. We showed you these graphs in Chem 1. This is an activation energy graph. Again, activation energy is referring to what's the minimum amount of energy that they need in order to break apart. I mean, we could supply more and they'd still break apart. And there's at some point, how fast can I throw a ball in a window before it breaks? And if I throw it faster, it's still gonna break. So on this graph here, sorry that's a little blurry, you start off with reactance. It climbs up a hill. Once it has enough energy at the peak of that hill, it can form products. And the two things shown on here is that first top hill. I guess since I'm recording, I can use my cursor to show. This hill right here is the activation energy, the E sub A, energy activation. The difference between the reactants and the products would be how much energy is either taken in or released in that reaction. In this particular one, energy is released because the products are at a lower energy state than the reactants are. I don't know if you remember from Chem 1, and this is tricky because our energy unit doesn't start until second semester. However, we need to be able to recognize these graphs. This is an exothermic graph. Exo meaning exit or leave, thermic heat or energy. So this graph is showing there's a net loss of heat in that reaction. So heat is released in that. Every reaction requires an input of energy, and every reaction has an output of energy. It's just what is the difference between the two that determines whether a reaction is endothermic or exothermic. And in this particular one, this is exothermic because more energy is released when we go to our products than is put in to start off. So if this is an activation energy curve for an exothermic reaction, here's one for an endothermic reaction. There's more input than output. Now I have handwritten here an arrow to this peak right here. That peak is referred to as the activation complex. I'm going to show you an animation about this in a little bit, but typically when you write a balanced equation, heck, even the equations I have up on the whiteboard right now, this is a simplified version of what's going on. Because usually what happens is reactants get close enough together and they form kind of this middle stage, often referred to as an activation complex. And what will happen with that activation complex then is it will break down into the products. Again, I imagine if we look at those goal sheets that I give you, it's going to refer to things like this when we talk about energy profiles, which this is just the energy profile that's referring to as activation energy curves. Your textbook today, when you do your reading guide, is going to show you a little bit more complicated activation energy curves because some reactions require more than one step to complete. So there's a step one hill. There's a step two, a second hill, and then you get to your final answer. So really those multi-step problems is one of the last things that we have to be aware of when discussing this. But one more time, just labeling wise, this would be an endothermic reaction. More energy is put in to go from reactants than is released to get to products. Or the products are at a higher energy state than the reactants. So this letter C right here shows the net change in energy, the net change. Because again, just like a net reaction that I started talking about at the start of class, this is the net difference between the two. Okay. Once again, the last thing that we need to consider here when talking about how fast reactions occur, because again, a higher activation energy would kind of mean that that reaction is going to take longer to occur, is how they hit. And I referenced this a little bit before with the baseball, but even the cymbals, if you don't crash the cymbals together the right way, they're not going to work. I mean, isn't there a way you can crash them together perfectly where they just suction together? That'd be bad. Or for some reason they decide to flip their hands around and hit the cymbals the opposite way. That would make no sense. So what I'm going to do to wrap up then is show some of their animations to express how these things work, because I like all three animations that they're going to go over. Now, the one thing I didn't talk about that the reading guide is going to talk about is a catalyst. And a catalyst is meant to speed up a reaction. In Chem 1, we talked about how it can lower activation energy. So if you think about those activation energy curves, it just creates a secondary step that is a little bit more efficient. So it makes it a lower curve. But I'm going to show you a little bit about that as well here. Let's get over to this. So let's start with activation energy.
When molecules collide, there must be a minimum collision energy for the reaction to occur. Lacking this energy, the molecules remain intact and no change results from the collision. The colliding molecules must have a total kinetic energy equal to or greater than the activation energy, which is the minimum amount of energy required to initiate a chemical reaction. Click on endothermic or exothermic reaction to view an animation of the energy profiles for each of these reactions. This is an energy profile for nitrogen dioxide, NO2, reacting with carbon monoxide, CO, producing nitrogen monoxide, NO, and carbon dioxide, CO2. Click on each of the regions, A, B, C, or D, as they appear to view the molecular changes that occur during each stage of this reaction.
Sorry that for some reason this doesn't actually fill up the board. You see the picture of the reactants right here. So step A.
As the two molecules approach each other, an attractive force begins to form between one of the oxygens of nitrogen dioxide and the carbon of carbon monoxide, which is indicated by the dashed line. The bond between the nitrogen and oxygen of NO2 begins to weaken, and the bond length increases. When molecules collide, they form an activated complex, which is a temporary species formed by the reactant molecules as a result of the collision before they form products. In this reaction between nitrogen dioxide and carbon monoxide, the activated complex is NO2CO. The activation energy, which is the minimum energy needed to initiate this reaction, is 132 kilojoules per mole.
So they all kind of came together, but once they come together, it's unstable because there's too many bonds occurring. Again, think back to Lewis Dot, how many bonds, and octet rule, and all that sort of stuff. So now things are going to start to break apart.
At this point in the reaction, the bond between carbon and oxygen continues to strengthen, and the bond between nitrogen and oxygen continues to weaken. A bond is now formed between carbon and oxygen. The bond between nitrogen and oxygen has broken. The products of this reaction are nitrogen monoxide and carbon dioxide. The products are more stable than the reactants. The products have a lower potential energy. In this type of reaction, heat will be released by the reaction to the surroundings. The heat released by the reaction is 226 kilojoules per mole. This is an exothermic reaction.
Notice that's a negative 226, representing negative energy released. That's another way to know that's exothermic. Here's endothermic.
This is an energy profile for nitrogen monoxide, NO, reacting with chlorine molecules, Cl2, to produce nitrosyl chloride, NOCl, and chlorine atoms. Click on each of the regions, A, B, C, or D, as they appear to view the molecular changes that occur during each stage of this reaction. As the two molecules approach each other, an attractive force begins to form between the nitrogen of nitrogen monoxide and one of the chlorines of the chlorine molecules. This attraction is indicated by the dashed line. The bond between the chlorines begins to weaken, and the bond length increases. When
Longer bonds are
molecules
weaker.
collide, they form an activated complex, a temporary species formed by the reactant molecules as a result of the collision before they form the product. In this reaction between NO and Cl2, the activated complex is nitrile chloride, NoCl2. The activation energy, which is the minimum energy needed to initiate this reaction, is 85 kilojoules per mole. At this point in the reaction, the bond between nitrogen and chlorine continues to strengthen, and the bond between the two chlorines continues to weaken. A bond is now formed between nitrogen and chlorine. The bond between the two chlorines has broken. The products of this reaction are nitrosyl chloride, NoCl, and chlorine atoms. The products are less stable than the reactants. The products have a higher potential energy. In this type of reaction, heat will be absorbed from the surroundings by the reacting mixture. The heat absorbed, or delta H, is 83 kilojoules per mole. This is an endothermic reaction.
Okay, so that reminds you of activation energy curves.
For simple reactions, for example those between atoms, the frequency factor A in the Arrhenius equation can be equated with the frequency of collisions between reacting species. However, for more complex reactions, the orientation factor must also be considered. More specifically, how are reacting molecules oriented relative to each other when they collide? The carefully studied reaction between potassium atoms and methyl iodide, CH3I, to form potassium iodide, and the methyl radical, CH3, illustrates the importance of the orientation of the collision. Click on correct or incorrect orientation of collision.
So two things to mention before I click on that. One is the narrator mentioned the Arrhenius equation. That's actually brought up on one of your topic sheets for today. However, it's not an equation that you ever have to plug it into and solve. The Arrhenius equation is just mathematically figuring out what's the activation energy for something. And it varies on temperature, so they have like a temperature variable within there. Second thing I want to mention is what the narrator said is if these are our two reactants, we're trying to make potassium iodide. And then CH3 is our other product. So if you think about that's what we want to make, it should hopefully make sense to you, especially after seeing that activation complex prior, that if they collide the correct way, they can make that. But if they don't collide the right way, they're not going to make that. So let's start with the incorrect orientation.
This reaction is most favorable when the potassium atom collides head-on with the iodine atom in CH3I. In this reaction simulation, the potassium atom collided with one of the hydrogen atoms of CH3I. With this collision orientation, few or no products are formed.
So if they hit the wrong way, they're not going to make anything. They have to hit the right way, correct orientation.
This reaction is most favorable when the potassium atom collides head-on with the iodine atom in CH3I. Otherwise, few or no products are formed.
Boy, even their diagram was nice because once the K hit the I, that means K is losing an electron to I, means potassium loses a shell, so they made the K get smaller, the I got a little bit bigger because it's more repulsion. But if you're trying to make Ki, it would make sense that the K and the I are the two things that have to bump into each other. Simply having the K bump into that methyl group isn't good enough. The last one I want to show you is about a catalyst. Again, a catalyst is something that speeds up a chemical reaction, and what you're going to see is it's going to briefly mention a biological catalyst, so something that you might hear about more in an AP Bio type class. But we can have non-biological ones as well. You'll see examples of that over the next few class periods, either with the reading guide or the, again, problems that I give you.
Catalysts are substances that speed chemical reactions without being used up in those reactions. In cells, catalysts are usually large globular proteins known as enzymes. There is a portion of an enzyme, its active site, that binds only to a particular molecule, its substrate. The substrate is a participant in the reaction catalyzed by the enzyme. The binding of substrate to enzyme causes a change in the shape of the enzyme, which in turn facilitates the forming or breaking of bonds by the substrate. The product of the reaction is released, and the enzyme is available once again. Because of the fit between substrate and active site, each enzyme is specific for a particular reaction.
Now, again, we aren't going to focus too much on biological catalysts, but the idea that it got used to help out, but then it's not used up. That's something that you are going to see that we are going to bring up as well a little bit more. Because if I look on your goal sheets here, again, energy profile is those activation energy curves, but then a catalyst should be on here as well. and it'll talk about many enzymes function in this manner. So it does talk about an enzyme a little bit, but we'll just talk about how it's trying to speed up something, but it's not being consumed. So now this sheet might not be one that I give you today. You might be picking this up later. However, your reading guide is going to end with talking about this topic as well.